All right, continuing with section 5.2, we're doing the sum and difference formulas for cosine. We haven't seen the ones for sine yet, but that's coming up. So in this problem, they want me to verify an identity. You remember doing those in the last section. So this identity says the cosine of alpha minus beta divided by cosine alpha cosine beta is supposedly equal to 1 plus tangent alpha tangent beta. Okay. So I may have mentioned in section 5.1 that as you get more practice with verifying identities, certain things start to pop out at you. And what pops out at me in this one is the cosine of alpha minus beta. We've just been talking about that. So what I am going to do is I'm going to start with the left-hand side. And I am going to replace cosine of alpha minus beta with the difference formula for cosine. Cosine alpha cosine beta plus sine alpha sine beta. Cosine cosine plus sine sine. Cosine cosine plus sine sine. Right? Okay. And then this is a pretty typical trick, especially notice that this is one expression. And if I keep my eye on the prize, I'm trying to get it to be two terms. So what that's suggesting is that I should take this fraction and break it into two fractions. And that's going to look like this. Okay. So it's like undoing addition of fractions. There's my common denominator. So instead of having this one big numerator on top, I'll just separate them into two separate fractions. Okay. And now I think this is all kind of coming together. So here I have something divided by itself. That's how I'm going to get the 1. And then over here, notice you have a sine alpha over cosine alpha, which is tangent alpha. And you have a sine beta over cosine beta, which is tangent beta. I think we got it. Okay. Let's see. Do I have the ending on here? I kind of hope I do. I do not. Okay. All right, so we are almost at the end. Here's my 1. Here is my tangent alpha, tangent beta. And there it is. Okay. 1 plus tangent alpha, tangent beta. That's exactly what we were trying to show. All right, so here we see all of our sum and difference formulas for cosines and sines. Number 2 is the one that we've just been going over. I'm not 100% clear on why they introduced this one first. I think it might be because it's the easiest one to prove. I haven't tried to do that in a while. It's just a guess. I'll just mention this without going into a lot of detail. If you know either one of these for cosine, it's pretty easy to derive the other one. So for example, let's say that you know this one. This is the one we've been going over. And you wanted to derive a formula for cosine of alpha plus beta. What you could do then is write out the formula for cosine of alpha minus negative beta. In other words, just replace all the betas with negative beta, and then use the even and odd properties of cosine and sine. So what ends up happening is this term stays exactly the same, and this term flips to the opposite. Okay. So notice with cosine, all right, it kind of goes cosine, cosine, sine, sine, but then the SIGN in the middle is opposite of whatever's here, right? Now with sine, S-I-N-E, it's a different story. So the sine addition formula, sine of alpha plus beta, first of all, the SIGNs are the same for sine. Addition has a plus and subtraction has a minus. So instead of going cosine, cosine, sine, sine, this one goes sine, cosine, cosine, sine, sine, cosine, cosine, sine, sine, cosine, cosine, sine. So I call that the sine rhythm. Okay. And that is literally how I remember these identities to this day. I also got that from my classmate 100 years ago. Not the GIF, just the little chant. All right. Okay. So let's see what we can do with the addition formula for sine. So 5 pi over 12. That is not, I don't think, an angle that we have ever talked about before. Does not appear in my unit circle. Okay. But we can still find an exact value for the sine of 5 pi over 12 using the fact that 5 pi over 12 is pi over 6 plus pi over 4. And maybe it would be worth spending a minute talking about why is 5 pi over 12 pi over 6 plus pi over 4. It's because if you get a common denominator, which would be 12, you do that one by 2 over 2, you do this one by 3 over 3. Right? This one becomes 2 pi over 12. That one becomes 3 pi over 12. So we're really talking 2 pi over 12 plus 3 pi over 12 is 5 pi over 12. Okay. All right. So if you need to find the exact value of sine 5 pi over 12, you are going. So let me take this one step at a time. I'm not crazy about when these things, show so many steps all at once. It's too hard to change it though. So the sine of 5 pi over 12 is equal to the sine of pi over 6 plus pi over 4. That's because of this. Okay. And now using the sine rhythm, sine, cosine, cosine, sine, the sine of pi over 6 plus pi over 4 is sine pi over 6 cosine pi over 4 plus the cosine of pi over 6 sine pi over 4. All right, so I know that you can fill in all of those values in your sleep, right? The sine of pi over 6. Oh, okay, using that formula. The sine of pi over 6 is 1/2. The cosine of pi over 4 is root 2 over 2. The cosine of pi over 6 is root 3 over 2. And the sine of pi over 4 is root 2 over 2. Wish these were lined up a little better. Okay. All right, so now, whoops. Multiplying those fractions together, 1/2 times root 2 over 2 is just going to be root 2 over 4. Oh, they skipped a step. Let me see. You know what? I have been avoiding the pen lately. Let me try to use the pen. I really need more practice with the pen. Okay, first of all, I have to hit draw. Okay. All right, so 1/2 times root 2 over 2 is root 2 over 4. Root 3 over 2 plus root 2 over 2 is root 6 over 4. And since those two fractions have the same denominator, that's the same thing as saying root 2 plus root 6 all over 4. That is the exact value of sine 5 pi over 12. All right. The next three examples are related to each other. I was just telling the class that's sitting here in front of me. And so the first piece of doing that problem is to find the cosine of alpha, given that the sine of alpha is 4/5 and the sine of beta is 1/2. And they're also telling me that alpha is in quadrant 2 and beta is in quadrant 1. Okay, well, I don't think this particular problem has anything to do with beta. I think we can ignore that. All right, so here we go. You might remember doing problems like this in chapter 4. So first thing I'm going to remember is that the sine is y over r. So this is using the definition of trig function at any angle from section 4.4. So if y over r comes out to 4/5 and alpha is in quadrant 2, I can draw a picture of that. There's the picture. And we remember that the cosine of alpha is x over r, right? So I need to find x using the Pythagorean theorem. So x squared plus y squared is r squared. We know y is 4. We know r is 5. I solve that thing for x. Now remember, and it helps to look at the picture, if x squared is 9, normally that tells you that either x is 3 or x is negative 3. In this case, x is negative 3 because this angle is in quadrant 2, right? So now we know x is negative 3. We want to find the cosine of alpha. Oh, shoot. Sorry. I thought there was going to be stuff all over here. I forgot. The cosine of alpha is x over r. X is negative 3, r is 5. The cosine of alpha is negative 3/5. Okay, the next example is very similar. Given the exact same information that we had in example 4, we want to find the exact value of cosine beta. So if you're watching this at home, I'm going to ask you to pause the video and try to do that the same way we did example 4. And then we'll come back and compare notes. Okay, so hopefully you've had a chance to try that. Again, very, very similar to example 4. First of all, the sign is still y over r. So y over r is 1/2. This time beta is in quadrant 1. So that picture looks something like this. And we're looking for cosine beta, and that's x over r. So I do need x. Using the Pythagorean theorem, x squared plus y squared equals r squared. Gives me x squared plus 1 squared equals 2 squared. And that means x squared is 3, which, without any other information, would mean that x is either the positive or negative square root of 3. But since we know that beta is in quadrant 1, this time we're looking for the positive square root, right? So x is the square root of 3. That makes cosine beta square root of 3 over 2. Okay, so this is what we've been working up to. So all of our hard work in examples 4 and 5 is going to pay off now. So we're given that the sine of alpha is 4/5. Alpha is in quadrant 2. The sine of beta is 1/2. Beta is in quadrant 1. That is enough information to find the exact value of cosine of alpha plus beta. Okay. So remember, the cosine rhythm, cosine, cosine, minus sine, sine. Cosine is the one that changes SIGN in the middle when you expand it out. Okay, sorry, I have these things coming up in a funny order, and I take responsibility for that. I'm the one that did this. All right. So from our previous work, well, we're given these two things, and then from our previous work, we know that the cosine of alpha is negative 3/5, and the cosine of beta is root 3 over 2. So now, the cosine of alpha plus beta is cosine, cosine, minus sine, sine. And now you just fill all these things in. See, now it makes sense why they asked me to find the cosine of alpha and the cosine of beta, right? Because they knew I was going to need these things. So we found that the cosine of alpha was negative 3/5. We found that the cosine of beta was root 3 over 2. And we were given sine alpha and sine beta were 4/5 and 1/2. So you put that all together. Cosine alpha times cosine beta is negative 3 root 3 over 10. And 4/5 times 1/2 is 4 over 10. Notice they didn't simplify the fraction. That was very clever of them, actually, because they're keeping these with the same denominator. Okay, so negative 3 root 3 over 10 minus 4 over 10 is negative 3 root 3 over minus 4 all over 10. All right, similar example, we just found the cosine of alpha plus beta, given this same information. So now they want me to find the sine of alpha plus beta. So once again, if you're watching at home, I'll ask you to pause the video. Try this one using the addition formula for sine. Okay, so again, very similar to what we just did. It's just a different formula. So we're given the sine of alpha is 4/5, the sine of beta is 1/2. In examples 4 and 5, we found these two things. All right, so you just have to use the correct formula. Remember the sine rhythm, sine, cosine, cosine, sine. The sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. Notice one time you're taking the sine of alpha, the other time you're taking the cosine of alpha. All right, so the cosine and the sine get switched, but the alpha and the beta, they stay where they are. So the sine of alpha is 4/5. The cosine of beta is √3/2. The cosine of alpha is -3/5. The sine of beta is 1/2. You put that all together, 4/5 times √3/2 is 4√3/10. And then -3/5 times 1/2 is -3/10. Those have the same denominator. The final answer, exact value of sine alpha plus beta is 4√3 minus 3 all over 10. All right, so it turns out that there are sum and difference formulas for tangents. As I may have mentioned, maybe I didn't mention it in this video. Oh, I think I might have said this. I can't remember. Anyway, the formula for tangent is not quite as important as the ones for sine and cosine because, for example, if they ask you to find the tangent of 5 pi over 12, well, yes, you could use this formula, or you could just use your sum formulas for sine and cosine, find the sine of 5 pi over 12, find the cosine of 5 pi over 12, and then use your quotient identity. Okay, so this is not a formula that I even, if somebody came up to me and asked me what is the sum formula for tangent, I'm not 100% confident I could remember it off the top of my head. So I don't think it's one that's super important for you to remember. But I would like you to at least see it. And let's see. Forget about that. Putting this into words is not helpful. And I have never heard of a tangent rhythm. So if you want to try to come up with some easy way to remember this, I will leave that up to you. Okay, that's what I thought. So the difference formula for tangent, it just changes all of the signs, SIGN, inside. Okay, so with the addition formula, you have plus on top, minus on the bottom. The difference formula, it's reversed. Okay. All right, so the example that I have for this, and by the way, this is something we already know. We already know that the tangent of x plus pi is equal to the tangent of x, and the reason we know that is because we know the period of the tangent function is pi. Okay, and so this is true because of that fact. That's exactly what having a period of pi means. Every time you add pi or add a multiple of pi, you just get the same value back. Okay, but it's still a nice problem because it'll, help convince me that that sum formula is correct. So the way that we're going to do this is we're going to start with the tangent of x plus pi. And we're going to use our addition formula to write that as the tangent of x plus the tangent of pi over 1 minus tangent x times tangent pi. And of course, the tangent of pi is 0, right? So that leaves me with tangent x plus 0 over 1 minus tangent x times 0. So this is going to go bye-bye and just leave me with this, tangent of x over 1, which of course is tangent of x.